All right, I want to just dip our toes a little bit into section 2.5, and just hopefully briefly explain the precise definition of the limit. I just kind of want to demystify it a little bit, just kind of show you what it means. I don't want to spend too much time in getting super deep in it, but basically it kind of gives us an algebraic and kind of symbolic representation of what we've been talking about more in a conceptual and kind of intuitive way, right? We've been talking about the limit is like as you get super close to a number, on the x-axis, what is the output approach, or what does it get super close to, right? And so we've kind of used those kind of more vague and informal terms, and this is the kind of the more formal definition of what it is. Okay, and so here we have let f of x be defined for all values where x is not equal to a over the open interval containing a. Okay, so the function has to be defined on everything but a in a certain interval, right? Okay, and so this is, remember, an open interval, so that means we can have parentheses on either side. Okay, so the function has to exist on some interval on either side of a, basically. Okay, and we're letting L be a real number, so that's the limit, right? That's the value that the limit equals. Okay, and so we're saying for every value epsilon, this is epsilon here, that's greater than 0. So we're just saying for any number that's bigger than 0, right? For any value that's bigger than 0, there exists a delta that's greater than 0. Okay, so a positive number there, right? So we're saying there's a positive number epsilon, a positive number delta, such that, okay, 0 is less than the absolute value of x minus a, and remember a is the value that we're approaching here, okay, is less than delta. So let me just stop for a second. So this right here, an absolute value of a difference, is the distance from one point to the other, right? Or is the distance from one value to the other. And so what this is saying the distance from x to a, or a to x, right? From x to a, or a to x, right? And so the absolute value of a difference is always the distance from one number to the other. Okay, and so so that's what this is. So they're basically saying that the distance has to be greater than 0, right? This distance has to be greater than 0, and it has to be less than some positive number, right? And that's any positive number. So you could pick 0.1 or 0.5 or 100 or whatever. So there has to be a value where this distance is greater than 0, but also less than some positive number. Okay, and remember that we can always find values in between, right? We just talked about finding a value between 2.01 and between 2 and 2.01, right? So we can always find a value between any two numbers, right? There's an infinite amount of values between any two numbers. The other thing that this says, this distance has to be positive, right? So remember, when we're looking at the limit, we're not just necessarily plugging in that value. Sometimes we can use direct evaluation, and that's something that works. But in terms of the definition of the limit, we're saying we don't want to actually plug that value in. We want to get super close to it without actually reaching it, right? And so this right here means we're not actually reaching it, okay? And this here means, this side here means that we can get super close, right? Like there's always going to be some value. This is always going to be between any value, right? So you could pick a number, like delta could be 0.000001, right? And we're going to find a value that's in between that, right? That's closer than that to our value for a. Okay. Anyway, hopefully that kind of makes sense. And then on this side, we're saying that the distance from the output to the limit is less than some value that's positive, right? So once again, this could be a super small value, and we're saying that we're getting, the distance from the function itself to the actual limit is getting super small, right? Or is getting less than some real number value, right? And that could be any real number value that's super small, okay? And so basically all this is saying is, as we get closer, as the distance between x and a gets super, super small, even though it's positive, it's going to get super, super small, then the distance from the output to the actual limit is going to get super, super small. Okay. And so this table kind of gives us a representation of that. But let me just show you the graph, and I'll let you read the table. It's in the book too. But this is kind of an idea of what's happening here is, no matter what values we pick for epsilon or delta, we can keep picking smaller and smaller values, and they'll get closer and closer together, right? So we're saying, hey, if we get within epsilon, or let me start this way, if we get between if we get some value delta away, as we get closer and closer on the x-axis to a, then we're going to get some epsilon value away from the actual limit, as the function gets closer and closer to L, right? And so we can just keep closing in on these values on the x-axis, and that'll keep closing in on these values on the y-axis, right? And so that's all that's saying. Basically, what this definition is saying is, as we get closer to this input value A, we're going to get closer and closer to this output value L, okay? And so that's basically what the formal definition is. It's actually saying the same thing we've been saying the whole time, is as we get closer and closer to the input value, then the output value converges or gets closer and closer to a certain value, a certain output value, and that's what the limit is, right? So this is kind of a real mathy formal way to say that. And if you want to challenge yourself, definitely check out some of the questions and examples, further on down what the assigned reading is. But I just wanted to kind of just present this and just kind of give you a real rough idea of what it means. So that, if you see it later on, or when you get to your college calculus class, that, that this is a little bit demystified, even though it looks a little strange or foreign. Hopefully it'll make a little more sense to you.